Okay, a while back we talked about inverse functions, and I want to hit the high points of that before we talk more about inverse trig functions. So if you got two functions and they're inverses of each other, they undo each other. Their graphs are mirror images across the line y equals x, and the last part is they are one-to-one, or in other words, they pass the horizontal line test. Now, obviously, the trig functions don't pass the horizontal line test. If we graph them out here, let's see, I got sine, cosine, and tangent all graphed here. And if I put this line across here, it's going to hit all of these graphs in infinitely many places. So it does not pass the horizontal line test. So what we're going to do is we're going to just choose a portion of the graph to use to make the graph one-to-one. Basically, we're going to restrict the domain here. Before we do this with trig, let's talk about this for a second. You know, f of x, let's say you have y equals x squared and y equals square root of x. You know, in some sense, those are inverses of each other, but not quite, because y equals x squared, if you graph it out, you get this. And that's not one-to-one. If we want to define this as its inverse, what we'd have to do is come over here and get rid of 1/2 of this. So if we get rid of that bit, now y equals x squared, if we restrict this where x is greater than or equal to 0, by restricting the domain, now we've got two functions here that are inverses of each other. We're going to do the same thing down here for sine, cosine, and tangent. Notice what we had to do before was, or what we did up here on the sine, or I'm sorry, on x squared, we got rid of half the graph. We left exactly one piece that covers the entire range. We're going to do the same thing down here on the trig functions. For sine, now it's kind of arbitrary how we do this. Notice I put the we in, I put an asterisk there. It's not us, like me deciding this, or us in the class. This is sort of the convention that's been used. So we want to pick a portion of the sine function that covers everything from -1 to 1. So we're going to use this from back here up to there. And for the cosine function, we're going to use stuff from here down to there, because that gets everything from -1 to 1. And on the tangent function, we need to pick one of these swishes, and we're going to use this one here, the one in the middle. Now, if you look at this, what's going on each one of these is we're picking, well, for sine, what we've got here, this is from back here to here. And if you look at that, each one of these tick marks, or each one of these grid marks, is pi over 2. So for sine, we're using the interval from -pi/2 to pi over 2, from here to here. Cosine, we're using from 0 to pi from 0 to pi. Cosine, and that should actually be a closed bracket, not an open bracket. And then for tangent, we're again using -pi/2 to pi over 2. So essentially what this means is if you take the inverse trig function of a positive number, it's going to give you something from quadrant 1. Here, here, or here. If you take the inverse trig function of a negative number, if it's sine or tangent, it's going to give you something back here. But if it's cosine, it's going to give you something over here from quadrant 2. And that's essentially what all of this stuff here says. All right, so let's look at this. Inverse sine of -1/2. The way we do this is the answer is going to be negative. And for a second, let's pretend this negative isn't here. Inverse sine of 1/2 would be pi over 6. But the negative says we've got to bop it over into quadrant 4. Inverse sine of a negative means we're in quadrant 4. So it's going to be negative pi over 6. Inverse cosine of negative 1/2. Now, inverse cosine of a negative number gives us something in quadrant 2. So for a moment, pretend the negative's not there. If this were just inverse cosine of 1/2, the answer would be pi over 3. But what this means is we've got to draw a reference angle of pi over 3 into quadrant 2. So going around here, this angle is 2 pi over 3. So I shouldn't have written that up there. This is 2 pi over 3. Okay, what about this? Inverse tan of square root of 3. Well, if it's a positive number, there's really nothing to do. All I'm going to do is, on my calculator, inverse tan of square root of 3. Honestly, I know it's either pi over 3 or pi over 6. I just never can remember which one it is. So I put in square root of negative 3, take its inverse tan, and it gives me 60. Now, I want to give my answer in terms of radians. So 60 degrees is pi over 3. I'm going to put in another problem down here. If we had inverse tan of negative root 3, that would just be negative pi over 3. All right, inverse sine of negative 1. That's going to be in quadrant 4. Well, actually, this is a quadrantal angle. Honestly, the way I would solve this is not how a lot of people would do it. But sine looks like this. And I know this is supposed to be in quadrant between minus pi over 2 and pi over 2. So the answer to this is minus pi over 2. And if I stick that in my calculator, let's see, 0.5, negative 1. I do the inverse sine. Sure enough, it gives me negative 90 because I've got my calculator in degree mode. So, in other words, down here, for positive arguments, argument being the thing we're plugging in, we're just doing a reverse lookup on the special angles. For the negatives, we have to look at the reference angle and put it in the correct quadrant. So what that means is for cosine is really the only one that we have to be careful on. You have to throw that reference angle into the second quadrant. For sine and tangent, you can just put the negative on the front because they're odd functions. Maybe we should do one more of these. If we were to do inverse cosine of, there's only a couple of things we can do here. If we did inverse cosine of negative root 3 over 2, the root 3 over 2 tells me that my reference angle is going to be pi over 6, and it's going to be in quadrant 2. So that's pi over 6 down there. So my big angle here is 5 pi over 6. All right, we'll look at evaluating composite functions in the next video.